So we're going to look at the reactions of the alcohols, both the formation and the reactions that they undergo. We already know some of the reactions of alcohols. For instance, we have learned how alcohols can be changed to halides, and we also know that halides can be changed back to alcohols by SN2 reactions or by SN1 reactions. We have seen that alcohols can be changed to ethers by SN1 or SN2 reactions. We have seen how alcohols can be dehydrated and made into an alkene. Now what we're going to do is we're going to look at the oxidation and reduction relationships of alcohols with ketones, aldehydes, carboxylic acids, and esters. And we're going to see that we're going to be able to define what's oxidation and reduction, and then we're going to be seeing what are some of the oxidizing and reducing agents and what are their selectivities and reactions. Okay, here's a review of a couple of the reactions that you already know. You know that alkenes can be made into alcohols by either hydroboration or oxymercuration. And of course you know that the hydroboration gives you anti-Markovnikov addition and syn addition. With the oxymercuration, you get Markovnikov addition. If we have an alkene, we can turn it into diols. We can do that either with osmonium oxide followed by sodium bisulfite, and that gives us a syndiol. And we know that we can change an alkene into an epoxide, and we can open up an epoxide with acid and water to give us a transdiol. The new reactions that we're going to be looking at are oxidation and reduction. And the first one that we're going to look at is the reduction of a carbonyl to an alcohol group. And this symbol right here, the brackets around the H, that's a symbol that means reducing agent. So we're not specifying what reducing agent, we're just saying some kind of reducing agent. We do the same thing for oxidizing agent, where we put the capital O inside a bracket, and that means some kind of oxidizing agent. So what are some of the specifics? Well, we can reduce an aldehyde, notice it's on the end of a chain, into a primary alcohol, which is also on the end of a chain. Or we can reduce a ketone, which is a carbonyl in the middle of a chain, to a secondary alcohol, which also is in the middle of a chain. The reagents that we will use for this is sodium borohydride or lithium aluminum hydride. Sodium borohydride is a gentle reducing agent. It reduces aldehydes and ketones quite well, but it's not violent in its reaction. We can even mix it with water if it's basic water, and it doesn't violently react. There's lithium aluminum hydride is a reducing agent that's a lot more powerful and can be violent when you use it. For instance, if you mix it with water, there's a violent reaction. And so there's reasons for using both. The examples shown here are sodium borohydride, reducing an aldehyde to a primary alcohol. Of course, because sodium borohydride would give the basic compound, the alkoxide, after the reducing step, you then protonate that with acid afterwards. So you're always going to see after these reducing agents, the hydride reducing agents, that you're always following with an acid wash. The example shown in the bottom is that a ketone is taken to a secondary alcohol. If you look at the comment at the bottom of these three comments, you will see it says both add the equivalent of a hydride. And so you can look at it's equivalent. What they do is equivalent to taking a hydride, which looks like an excellent nucleophile, and adding it to the carbon in the carbonyl, which is effectively what they do, but that's not the mechanism. Here's a picture of that. Remember, this is not the mechanism. The mechanism is a little bit more complicated, but this is an effective view of how a hydride will reduce a carbonyl. The hydride, sodium borohydride or lithium aluminum hydride, will basically add a hydride to the carbon in the carbonyl, and when it's through with that reaction, it's kicking the pi electrons up onto the oxygen. You have this alkoxide intermediate that stays there until you wash with acid, which then protonates the oxygen. You can reduce other oxygen-containing functional groups such as carboxylic acids and esters, but remember, sodium borohydride is a very gentle reducing agent, and it's only going to work for aldehydes and ketones. Something that's a lot more aggressive, like lithium aluminum hydride, is needed to take a carboxylic acid and reduce it to an alcohol, or to take an ester and reduce it to an alcohol. So lithium aluminum hydride will take both acids and esters and take them down to primary alcohols. Again, you see there's an acid wash after each one, because what would be the product after lithium aluminum hydride would be the alkoxide, not the alcohol, until you wash with acid. Now, we already know how to convert alcohols into alkyl halides. If you take a tertiary halide, you can treat it with hydrochloric or hydrobromic acid, and it will give you the chloride or the bromide, and this goes through an SN1 reaction that has a carbocation intermediate. We also know that primary and secondary alcohols can be converted to the chlorides or the bromides by thionyl chloride or phosphorus tribromide. Usually we have pyridine along with the thionyl chloride, but here it's not showing it. Regardless, it would work. You just would have a lot of acid left over afterwards. Okay, so primary and secondary alcohols are made with thionyl chloride or phosphorus tribromide through an SN2 reaction. We've already seen this reaction of the dehydration of alcohols to give alkenes. What happens in this reaction is we remove water to form a pi bond. The alcohol, the mechanism goes by the alcohol is protonated by strong acid. Water leaves, leaving a carbocation behind, and then the proton leaves to put the double bond in place. We use concentrated sulfuric acid or phosphoric acid, but the problem with this is that often you have many miserable, complicating side reactions, and you often get polymeric crud in the bottom of your flask when you try to do this. Tertiary alcohols are readily dehydrated with acid, and that's because they undergo the E1 reaction that is the mechanism easily, because it forms a tertiary carbocation. If you're trying to do this to a secondary alcohol, you have a lot of problems because it's going to require a lot of heat, and many times other functional groups will react, or sometimes the molecule falls apart. Primary alcohols just actually are really bad for using for this, because the primary carbocation is very hard to form. You have to use high temperatures, long times, and you often have a lot of side reactions that make this not practical at all. You get very little yield on it. And so what is it you're depending on? The carbocation intermediate. And so the only real practical compound to do an acid catalyzed dehydration on is a tertiary alcohol. The others give you too many problems. We can oxidize alcohols. When we oxidize a primary alcohol, we can take it to an aldehyde, and depending on the reagent, it may go even further to the carboxylic acid. Secondary alcohols can be oxidized to a ketone, and tertiary alcohols, because they have no proton on the carbon that the alcohol group is on, they do not undergo oxidation. Because in oxidation, what you always have is a proton that is on the carbon attached to the oxygen is removed by the oxidation. So you can see that an aldehyde, because it has two hydrogens attached to that carbon, can undergo a two-step oxidation. A secondary alcohol, because it has one hydrogen attached to that carbon, can undergo a one-step oxidation, but tertiary alcohols cannot undergo them. Now, you have many reagents that you can use. The cheap ones are potassium permanganate, chromate, and sodium dichromate. And there's some more selective, more expensive reagents to be used. These here that are shown always take the alcohol down to the highest oxidation level. So these reagents here would take a primary alcohol all the way down to a carboxylic acid. Secondary alcohols have to stop at the ketone, so these would take a secondary alcohol to a ketone. And of course, even these harsh reagents up here will not oxidize a tertiary alcohol. This is something that I just informed you. If you have a tertiary alcohol, it will not undergo an oxidation reaction. The carbon that is attached to the hydroxyl group, we call that the alpha carbon, must have at least one hydrogen for oxidation to occur. So this is chromic acid, which is along the same lines as the one oxidizing reagents I just showed you, will not oxidize a tertiary alcohol. Neither will potassium permanganate, neither will sodium dichromate, neither will chromium oxide. So here's the oxidation of a primary alcohol. Notice we have some other functional groups there. A primary alcohol can be oxidized to an aldehyde, and it stops at this level with something called pyridinium chlorochromate, which is more commonly called PCC. Dichloromethane is a solvent. It is not necessary to even have to write that, but we sometimes do. Remember, other reagents that we might use here, like potassium permanganate, chromate, sodium dichromate, or chromic acid, all of those will take it down to a carboxylic acid. To get it to stop at an aldehyde, you have to use pyridinium chlorochromate, or PCC. Secondary alcohols can be oxidized with the harsh ones, for instance, sodium dichromate and acetic acid. But if there are other functional groups in there that may be sensitive to, let's say, acid, you may not want to use that. So you can use PCC, the gentle oxidizing agent, and it would take a secondary alcohol to a ketone quite well. Phenols can be oxidized, but notice there is no, at this carbon right here, there are no hydrogens, so it's not oxidized in the typical way. If you look at phenol, we can oxidize it, and what do we get? We get what's called a quinone. Notice we have 3 double bonds and 1 bond to a heteroatom. Here we have 2 bonds to a heteroatom and 4 double bonds. So we've had an increase in oxidation. This is an important reaction. Quinones are important in biology. We find quinones in nature. This is a quinone that we find in nature. It will be reduced by NADH, and it makes what's called a hydroquinone. NADH is oxidized by quinones down to NAD. Of course, this is a redox reaction, and whenever you have reduction, you also have oxidation occurring. Then the hydroquinone that is formed can be oxidized by oxygen back to a quinone, and so you find you have an oxidizing agent in the quinone, and which is regenerated then by oxygen. What are the outcomes of these reactions? Notice this is a secondary alcohol, and we've got sodium dichromate. If I treat this with sodium dichromate and acid, you make chromic acid, which then oxidizes this. What does it oxidize it to? The ketone. Here again, I have a secondary alcohol. Here we have chromium oxide and pyridine. What's going to happen? You're going to make the ketone again. Now I have a primary alcohol. A primary alcohol with acidic dichromate. What do we get? We're going to get oxidation all the way down to the carboxylic acid. Notice we have an intermediate of an aldehyde, but that aldehyde is only, you can't stop it, can't collect it. It immediately reacts with the chromic acid that's in the solution all the way down to the carboxylic acid. Here we have a primary alcohol being treated with PCC. What do we get as a product? The product here will be an aldehyde. Here we have a primary alcohol, and we're treating it with acidic, basically chromium with an acid. Chromium with an acid will give carboxylic acid. It oxidizes it all the way down as far as it can go to the carboxylic acid. So what reagents would you use to take these compounds to the alcohols shown? Well, this is a secondary alcohol to take a secondary, this is a ketone to take a ketone to a secondary alcohol. You can use sodium borohydride, or you can use lithium aluminum hydride. Here we have an aldehyde. To take an aldehyde to a primary alcohol, what do we have to do? We can use either sodium borohydride or lithium aluminum hydride. Either of these will work for this step. When is it that we have to use lithium aluminum hydride? When we have either a carboxylic acid or an ester, lithium aluminum hydride is going to be the reagent needed to take that functional group down to an alcohol. So what reagents do we need for these steps? For this first step, we have a carboxylic acid. To change a carboxylic acid to an alcohol, what do we use? Lithium aluminum hydride, followed by an acid wash. To take this aldehyde to an alcohol, what can we use? Either sodium borohydride or lithium aluminum hydride. To take this acid to this alcohol, what do we have to use? We can use lithium aluminum hydride only. Sodium borohydride will not work.